So recently I've been playing a game called Wordle. I think I came across Wordle because Tom Scott mentioned it on his newsletter that he sends out every Monday or so, and I clicked on the link. I played it. It was great fun. I have about a 2-week streak at the moment. Not that long of a streak because I just started playing with it, but it's really fun. Like, it's a puzzle game. It's a word puzzle game, and it's really fun. And it's become a bit of a viral hit in a way. Like, I've started to see people posting about it on social media and so on nowadays. And when I looked at the game, I thought to myself, like, there must be a way that you could code up something or find some algorithm that helps you win the game, right? Using a bit of computer and a bit of statistics. And I had a bit of time during the weekend, or at least I wanted to take a break during the weekend from all the research work. And I think it was a project, this sounded like a project that could be done in a weekend or maybe even in a day. So I tried coding something up and I spent some time making this video. So this video is going to be a video about me going through the process of making a solver for the game of Wordle using a little bit of statistics. And if my advisor's watching this video, don't worry, I'm still reading papers. Don't worry about that. So if you haven't played Wordle because you haven't seen it on social media, or you've been living under a rock, or you're just not into these types of games, let me quickly explain how the game works. To start the game, the computer will pick a random 5-letter English word. It will be a valid English word. So as an example, let's say the computer picked the word maths for some reason. Now, as a human player, your objective is to try to guess the word that the computer is thinking of within 6 guesses. You're allowed to guess 6 different words, and you have to try to get to the word that the computer is thinking of. Now, obviously, if you're just guessing blindly, it's going to be very difficult to actually get to the correct word by chance. So the computer sort of helps you out a little bit by giving you hints on how close your guesses are to the actual word. So if you guess a word, the computer will tell you whether a character you guess is already correct or it's almost correct. More precisely, when you guess a word, the computer will tell you which letter is already in the correct position, meaning that that is where the actual letter is in the word that the computer is thinking of. It will also tell you whether you guessed a letter which just happens to be in the wrong place, or whether you guessed a letter which is not even in the word at all. Now, in the actual Wordle game, they use color coding to denote whether a letter is in the correct position or in the word but not in the correct position and so on. But in our case, we're going to do it slightly differently. I'm going to use symbols to denote this. I'm going to use a string of symbols, as you can see on the screen. If a letter is in the correct position already, I'm going to use a circle to represent it. If it's in the word but not in the correct position, I'm going to use a cross, and otherwise I'm just going to use a dash. So here's a guess that we can make, the word taped. This would be the hint that the computer gives back to us. And here's some other guesses. Then you'll get other strings back from the computer. And using the guess information and also the hint that the computer gives back to you, you have to try to guess which word the computer is thinking of by using a bit of logic and deducing which word might be possible in a way. Now, of course, if you can get the correct answer within 6 goes, then you win. But if you don't get the answer within 6 guesses, then you just lose. So the idea of the solver that I want to make is I want to sort of make the perfect human player, sort of a program that will give the best possible guess. It will take in the information, it will make a guess that it thinks it's the best possible guess. It will take in the hint that is returned, it will process the hint, and then it will return the next best possible guess, and then give it to the computer and repeat the process, and then eventually be able to narrow down to which word the computer is actually thinking of. And it turns out that this is actually a pretty, I would say, pretty elegant answer in the end. So I do encourage you to stick around and look out for the maths. The first step is we have to actually try to code up the game, or code up something that will actually sort of pick a word, and then once we give it a guess, it will actually give out the correct hints and so on. So I made a program, I wrote a program that sort of is a bare bones Wordle game. Basically, the actual Wordle game has got like a nice user interface. This one's sort of just bits of code in a Python Jupyter notebook that sort of does what it's supposed to do. And I'm not going to bore you with the code. I'm going to link everything I do. I'm going to put it in a GitHub repository. I'm going to put that in the description. It's not the cleanest, but it will have everything I use. Now, another thing that we actually have to do as well is we have to get a list of 5-letter words that we want to use for our solver. Now, I don't actually know which 5-letter words the developer of the game uses, but you know, I thought I could just find any list of 5-letter words and just use it as sort of demonstration purposes. So the first thought I had was to just get a list of most common English words, and then sort of just filter out the ones which are not 5 letters long and just leave the words which are 5 letters long. And that sort of works, except it was missing out a couple of words, because obviously some 5-letter words is a valid 5-letter word, but it's not that common, so it doesn't appear in the list. Particularly the ones that were missing were the plurals, the word that aren't singular. I'm not an English major, I can't describe plurals properly, but the plurals weren't really there. You know, plurals are valid 5-letter words. I was thinking of just like shoving an S at the end of words that aren't 5 letters long, but like that, English is not a nice language, that doesn't really work. So in the end, what I did was I found a list of words that were valid in Scrabble. I'm going to link to that, the link to that source in the description. The repository was like really old. It was like 2012, like I think it was 2012 or something. But it had a nice list of words that were valid in Scrabble, and those included plurals and included common words that, you know, that I use. Like I checked against 5-letter words I know, all of it were there, so I thought that was good enough. And I filtered out all the words that were 5 letters long, and I kept it in a file. In the end, I have a list of this many words, English words, valid English words that were 5 letters long. About 8,000 and something, which was a lot of words. I'm not sure if the Wordle people actually used a list this big, but I figured out using a big list, you know, just makes the problem a little bit more interesting, so I kept it. So now I actually have a program that basically simulates a game of Wordle that you can sort of play with it like a human player. As a human guesser, the computer gives you the hints, basically like the game without the nice interface. So having the logic of the game, now we can actually try to make the solver, or the perfect human player. The question is, how do we do so? Now, before I actually get into the big statistical work, which is going to take up quite a bit of the video, let me give some symbols, right? Let's represent some of the elements of the game using a bit of mathematical symbol in a way. At first, we're going to have a massive list of words. We have a list of 8,000 or so 5-letter English words. I'm going to call this W0. W0 is a set of all the possible 5-letter words in English. This is going to be the list that the computer picks a random word from. So the computer, when it thinks of a word, it's going to pick a random word from this set, this list. And when we make a guess, we have to also make sure that our guess is a word in this set. It has to be a valid English word, and it has to be within this list of words. I'm also going to define another variable called S0, which just represents the size of this list 5-letter English words. I start the enumeration at 0 and you'll sort of see why eventually. Now let's also suppose A is the actual correct answer. Little a is going to be the correct answer that the computer is thinking of, the 5-letter word that the computer is thinking of. Now A obviously will be a random word that comes from W0. Now we have 6 different rounds, so in each of the rounds we're going to make a guess, and then the computer is going to give back a hint corresponding to the guess that we have based on the word that it's thinking of. So let's give symbols to that. So I'm going to define G1 as the first guess we make. This is going to be a 5-letter word that we make as a guess. So obviously G1 must be a valid 5-letter word. So G1 must be a word inside list W0. Now when we make a guess, the computer will give us back a hint. It will be a 5-letter hint telling which letter is correct, which letter is not, etc. I'm going to call this H1 as the hint. This is the hint that is given back to us, and it's going to be based on G1 and also based on A, the actual correct answer that the computer is thinking of. Now once we make a guess and the computer gives us back the hint, we're also going to try to track one more thing. We're going to track the possible words that it could still be, that is still valid, that fits the hint that we have. I'm going to call this set W1. W1 is a list of all the words that fits the hint that the computer gives us. So when we make a guess and then it gives us back the hint, we're going to filter out all the possible words and only leave the words that still fits the description. And I'm going to say that this list of words is W1. And similarly, I'm going to define S1 to just be the size of W1. As a concrete example, suppose the computer picks the word maths, M-A-T-H-S. So A is going to be equal to maths. And let's say in the first round we make a guess. The word that we guess is taped, as before. So we make a guess, the word taped, this is G1. Now H1 will just be the hint corresponding to the word taped, which will be this string. So now we have the first guess and we have the first hint. And using the first guess and the first hint, we can work out the list of words that are still feasible, the words which are in W1. So words like bait or faint or maths, they all fit the hint that the computer has given us. So all these words will be in W1. On the other hand, words like pales or words like gamer, these don't fit the description or fit the hint that we're given anymore. So these words will not be in W1. You can verify yourself that it doesn't fit the hint that we were given. Now, of course, this is only the first round. We have 6 different rounds. We're allowed 6 different guesses. So we're going to have to define more variables for those later rounds as well. But we're going to define them very similarly. So we can define G2 as the second guess. We can define H2 as the corresponding hint given after we make the second guess. And W2 being the words that remain after we make the guess and we get the hints back in the second round. So all the feasible words. But remember that this list of feasible words is going to have to also take into account which words were feasible in the first round. And then also similarly, we have S2, which is going to be the size of W2. So these are the list of variables that we have. One other thing that we can also sort of visualize is how these variables relate to each other. It's basically which variable influences another variable. So we can sort of draw a diagram looking a bit like this. So we're going to start off with W0, the list of all the 5-letter English words. This one can be treated as a constant, so we'll just leave it up there like that. Now, we're going to have to make a guess. We're going to have to make the first guess. And of course, this guess will be based on what we know about all the possible English words, right? We can sort of have a peek at what words is still feasible, in this case, every single one of them. And based on the information there, we can try to pick which guess is good. So we can say that the guess will be influenced by the list of words that we have. Now, after we made the guess and we get the hint, we can then use this information to deduce which words are still feasible based on the hint that we get. This is W1. W1 will be influenced by both the guess that we made in the previous round, G1, and also the hint that we get back. But it'll also be influenced by W0, which is the list of all the possible words that we had at the very beginning. So now we have W1 and obviously also S1 because that's just the size of the set W1. And in the next round, again, we'll make a guess. We'll make a guess at G2. And again, G2 will depend on which word is still feasible. We can peek at which words is still possible in our game, and based on that information, we can try to pick out which guess is a good guess. Now, of course, again, we make a guess, we get a hint, and using the information of the hint and the guess and the list of feasible words, we can then try to deduce which words are now feasible after that second hint. So we get a diagram sort of looking like this, and obviously we can continue on for another 6 rounds. So in one round, this is one round. This is making a guess and then getting a hint, and then making another guess, making another hint. This is sort of where we interact with the computer. We interact with the Wordle master, and using that information that we get, we can update what we think the feasible words are. Now, obviously, we also know that the guess that we make must be a valid English word. So actually, G1, G2, G3, etc., these all must be words taken from W0 at the very least, right? Because it has to be a valid word. We also know that H1 isn't actually random. It actually depends on the word that the computer is thinking of. The computer picked a word at random, uniformly at random, I should be more specific. It picks a word uniformly at random and then keeps that information somewhere. So H1 actually depends on which word the computer is thinking of, except we don't actually know which word the computer is thinking of. That's the whole point of the game. So in fact, to us, H1 is sort of somewhat a random thing, right? Like, we don't actually know what H1 we're expected to get when we make our guess. So in a way, H1 is based on the answer, but since we don't know the answer, H1 is sort of random. It's sort of something we couldn't really control. The only thing that we can truly control in our game is the guesses that we make. And we can pick which guess we make based on the information that we know. Now, without using any random strategy, what's a first guess at a strategy that we should use? Well, let's do this. Let's suppose in the first round we have all the possible English words. Just pick one of those out at random and guess that word, right? We can just guess any old random 5-letter word that we have. We get the hint. After we have the hint, we then filter out all the words that are no longer feasible. Filter all those words out, and then come back and then look at which word is still possible, pick out another word, and guess that word. And we keep repeating this until we get to the correct answer. Eventually, we'll pick out random words and then eventually be down to just one word remaining. Then we just say, now we've won. Of course, this is not that good of a method, and we will actually do better. So let's see how we can actually improve upon this very, very simple and very, very bad method. So let's focus on one round of the game. Let's consider the first round of the game, and all the other rounds of the game will be similar. In the first round of the game, we'll have to make a guess, get a hint, and then we can filter out the words which doesn't fit the hint, leaving us with W1. Now, the game that we have, we want to try to make sure that we get closer and closer to the answer. And the way we get closer and closer to the answer is if W1, the set of feasible words, gets smaller and smaller. Ideally, we want W1 to just equal 1. In that case, we know exactly what the word is going to be. That's obviously not possible. So we want to try to get W1 to be as small as possible. Or in other words, we want S1 to be as small as possible. So as I said, the only thing we can really control in our game is G1, the guesses, or in future one, the future guesses as well. In the first round, the only thing we can control is G1. We couldn't control which hint we get back, we couldn't really control W0, W1. So we want to find which particular guess will make W1 as small as possible. But again, since we don't know what H1 is going to be, we have to try to pick the G1, we have to try to pick the guess that makes the size of W1, the size of the feasible words, filtered out and become as small as possible in expectation. In other words, assuming we don't know anything about H1, assuming the word is random, H1 can be anything, which guess will likely give the best filtered out result. Before we actually get into the maths, because the maths is, well, it's just maths, let's actually try to understand or try to have a guess about which guesses are good and which guesses will be bad according to the metric that I've described. So the idea of a good guess is it will have to be a guess which allows us to rule out as many words as possible. And not only allow us to rule out as many words as possible, but also allows us to rule those many words consistently, rather than just a very unlikely chance of ruling out every single word or so. So, for example, a word like quick is not really that good of a guess. Why is it not good of a guess? Well, the C isn't that common of a letter in the English alphabet. K also isn't that common, and a Q's pretty much never really appears at all, apart from a really small subset of words. So if I guess the word quick, there is a very good chance that the hint I'm going to be getting is just going to say the Q's not there, the C's not there, and the K's not there. Which, well, I mean, it's nice, it rules out a couple of words, but it's not that useful because we already know not that many words has these three letters anyway. So ruling out these three words doesn't really give us as much information as maybe we would like to have gotten. On the other hand, if we guess another word, for example, stare, S-T-A-R-E, this is a pretty good word because all the 5 letters, S-T-A-R-E, they're all pretty common letters that appears in a lot of words. So by guessing this, there's a pretty good chance that you'll get a hint that maybe will help you be able to rule out more words. So the idea is we're trying to find words that will consistently be able to give us hints that will allow us to filter out many words. This is why the expectation is quite important, because we don't want it to just rule out the words once or on a small subset of words, but we want it to consistently perform and consistently be able to give us a smaller feasible set in the upcoming round. So now we'll actually try to walk through the maths. This bit can get a bit dry because it's just maths, but the payoff's amazing. So I do hope you stick around for it. So let's actually write out using a bit of probability notation. So what we're trying to work out is we're trying to work out the expected size of the feasible sets after the first guess. So I'm going to write this as follows. It's going to be the expected value of S1 given W0 and G1. What this means is we're trying to find what S1 is, what we expect S1 to be, the size of the feasible set, given the initial set W0 and also the guess that we make, in this case G1. So what this basically says is if we fix W0, we fix the initial set of 5-letter words in English, and we also fix a guess G1 in the first round. What do we expect the size of the list of words, the list of remaining feasible words to be after the first guess has been made? So how do we work this out? Well, the way that we work this out, the size of S1 will depend on which hint we get out from the Wordle oracle, the computer that we're playing against. So what we're going to do is we're going to sum over all of the possible hints. Now, when I say every possible hint, I really mean every single possible hint, from none of the letters being correct to one of the letters being correct but in the wrong position and one of the letters in the correct position, etc. All the possible hints that the computer can give back. And there are, if you like combinatorics, there are a total of 3 to the power of 5 of such of these possible hints, because there are 5 different letters, there are 5 different positions, and in one of those positions it can either give one of the 3 possible hints about that letter. So the summation will be over all of the possible hints. Now suppose we make a guess and then the computer gives us one of the hints. Suppose we fix this hint, right? We know exactly which hint the computer gives back. We can use this information to work out what S1 is. We can work out exactly what S1 is going to be equal to, because we know the list of the initial words, and we can do some filtering to work out how big the remaining feasible set will be. And we actually could also work out how likely we are to getting that particular hint, because we know what the possible answer might be. The possible answer comes from W0. So using that, we could work out which hint, how likely a particular hint will be. Given that we know that the computer picks out a random word from W0, we can work out how likely it is to give us that hint based on the fact that we know it draws a random word, and also the fact that we know what the guess is. And with these 2 pieces of information, we can complete the summation. We complete the summation. Inside the summation, we are going to be multiplying the probability of getting that certain hint given the list of words and also the guess we make. And we're going to multiply by the expected size of S1, given that we fix the hint that we have. And we're going to be summing this over all the possible hints. So by probability, this will be the correct expression that we're looking for. So the remaining thing to do now is work out what each of the 2 terms must be equal to. First term that we have, the probability of getting a certain hint. Well, that's pretty easy to work out because we know what W0 is. We know the list of all the possible words. And so we can work out how many of those words will fit the hint that we have and also fit the guess that we've made. And so the probability of getting a certain hint, very simply, it's just going to be equal to the number of feasible words that fits the hint and the guess, divided by the number of total possible words, which in this case is just S0. The other thing that we have to find is the expected number of remaining feasible words, given that the hint we have is equal to H. So given that we fixed the hint, and that quantity, very similarly, is just going to be, well, it's just going to be the number of words in W0, which matches both the hint that we have and also the guess that we've made, simply. And so now we have these 2 quantities that we're looking for, and so we can just plug it back in, and then we can rewrite the summation simply as the summation over all the possible hints for 1 over S0 times the number of words that matches that particular hint and also matches the guess that we made squared. And obviously for our solver, what we're trying to do is we're trying to find which guess G1 will make this quantity as small as possible. So in order to guess it, we can just simply try plugging in different values, different words into the expression, different guesses into the expression, and see which one gives us the lowest possible value. And that's basically it. This summation can be worked out, it can be worked out rather simply. It's a bit computationally expensive, I'll get to that in a second, but it technically could be worked out because we know what W0 is. We can just iterate through every single one of those and figure out which hint it corresponds to, and then just do the summation accordingly. And in order to just work out which guess will give us the lowest expected value of S1, we can just iterate through every single possible word that we have and just work out which one's the minimum value. And then we have that, Bob's your uncle. Now obviously, as I said, we can also generalize this to other rounds as well. We try to work this out for the first round, but we can also write a more general expression for round I for the future rounds. And this is basically the expression that we look like. Again, the expected value at the top is very similar, but instead of being based on W0, it's now based on the list of feasible words from the previous round. And also for the guess, it can just be any word. We try to work out the word that minimizes this quantity. So again, we iterate through all the possible words that we have. One slight question is, what list of words do we iterate over, right? On one hand, we could iterate through all the possible words because the game doesn't actually stop us from guessing whichever valid English word, or at least it doesn't if you're playing on easy mode. On the other hand, do you only maybe want to guess on the feasible words? If a word's not feasible anymore, why bother guessing it, right? Now it actually turns out it's actually better to not restrict yourself to just the feasible words. It's better to just guess allow the computer to guess using any possible English word. Let's suppose we have a game and we know which words are left. We know that there are 5 words that are possible remaining. And the words are bakes, cakes, fakes, lakes, and makes. Basically, we know that the last 4 letters is AKES. We don't know what the first letter is, and we're trying to work that out. Now, one of the strategy is obviously to just guess the word that are feasible. In this case, it means that we'll only guess using one of these 5 words. So I can guess bakes, and obviously it might be wrong, it might be right, and let's say it's wrong. Then I can go through the next word, make a guess, and so on. But as you can see, making a guess like this is a little bit more restrictive, because if I guess the word bakes, I can really only rule out one word, right? Like at the worst case, I can only rule out the word bakes. If I get lucky, I'll get the correct answer, but usually most of the time I'll get the incorrect answer. That's not very good. And in the worst case, you'll have to basically go through all of the words. In the worst case, you need 5 guesses to just guess that last letter, whatever that last letter is. What is better is to allow yourself to guess words which aren't feasible anymore, but might give you more information about that final letter. Let's suppose I guess a word like climb, right? The word climb has got C, it's got L, it's got M, and it's got a B. If I guess the word climb, then, well, I can get more information about what that last letter is, because the hint that I will get will pretty much indicate what that last letter has to be. So I can just then, in the next turn, get the correct word. It only takes me 2 guesses, even in the worst case. So obviously it's better to allow the computer to just guess any old random word as long as it's feasible. And it turns out that this is also a pretty good strategy for a human player to use as well. So basically, for a computer program, it is best to allow it to guess any feasible word. So guess any word from W0 rather than just guessing the words that comes from the feasible set in the previous round. Of course, sometimes the rules, if you're playing on hard mode, this isn't allowed, then, well, you can't really do much. But if you're playing in the easy mode, then it's better to allow the computer to do this. I've talked for too long. Let's actually look at some results. Now, in the results I'm going to show, I'm going to be comparing against the random algorithm, the algorithm where I just pick out any random feasible word and guess that word. So for the test, I've implemented the bad algorithm that I described at the very beginning, where we picked out a random word and then just guessed any word that is feasible, right? We pick out a word that's feasible, we guess, get the hint, filter out the words that no longer can be the answer, repeat it, and so on and so on. The actual game of Wordle only allows 6 rounds of guessing, but just as an experiment, I allow my program to continue guessing until it gets the correct answer. And I repeat 5,000 of these games because, well, we want to repeat quite a number of times, but I didn't want to go too long because otherwise it takes a while. So the first strategy that I said of picking out a random word and guessing it, well, obviously it didn't really do so well. On average, it takes about 4.9 rounds in order to get to the correct answer. And if we were to use this to play Wordle, it would have lost about 10 or actually more about 11% of the games it plays, which isn't that bad. I think an average human player maybe might do worse, I'm not entirely sure, but losing about 11% of the game, that's not really that good. Luckily, we have better methods. So I'm going to test both of the methods that I said. The first one where we only allow the computer to guess from any of the feasible words. If we actually look at the result that we get from the method of guessing a particular feasible word, which minimizes the quantity I described earlier, then the mean number of guesses that we need is 4.4, which is slightly lower, which is about half a turn on average lower than the random guessing. And in the 5,000 trials that we tried, the number of games that goes over 6 guesses is almost 400. So about roughly 8% of the game, less than 8% of the game, I think, if I did my math correctly, which is clearly an improvement from the strategy of picking out a random feasible word. But it doesn't really seem like a massive improvement. What really is a massive improvement is our final tweak, which is we allow the computer to guess from any possible English word rather than restricting it to a single feasible set. And in that case, we only need an average of about 4 guesses on average in order to get to the correct answer. And in the 5,000 trials, it turns out it would only have lost 2 of the 5,000 games. Only 2 of those 5,000 games required more than 6 guesses to arrive at the correct answer. And that is truly impressive. We can also sort of see how the actual game plays out. This is some of the games that it plays out. You can see that it's sort of quite short. It will always guess the same first word every time, and then it would always sort of like be very clever, be very strategic with how it guesses. It's really impressive to just watch how the computer guesses the words. So I want to show you guys the impressiveness of the solver. This is the sort of the quick command line / notebook solver that I made. So this is what I'm going to do. I'm going to see which guess the computer makes, and then I'm going to put it into the game of Wordle that I have open on my iPad here. So the first word that it tells me to guess is the word lares. So I'm just going to make that guess, L-A-R-E-S. I'm going to press enter, and then it's going to tell me that one of these letters is correct. Let me actually turn color blindness mode on, and let me remember that the red means that it's in the correct position. So in this case, the A is in the correct position, the other letters should not be there. So I can type this in. This means there'll be a dash, circle, dash, 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 and I press enter, and then it will give me the next hint. Now it goes from about 8,000 or so words down to 200 words, and the next guess it tells me to guess is the word minty. So I'm going to put that in again, M-I-N-T-Y, press enter. Then it tells me that these 2 words, these 2 letters, N and Y, are in the correct position. The T is not in the correct position, but it is in the word. Again, translate that into code for the hints. So dash, dash, circle, cross, circle, hit enter, and then, oh wow, one word left, and that's the word tangy. And thank God I used the solver, because I would not have known what that word means. So I can put that in, T-A-N-G-Y, hit enter, Bob's your uncle. You get the correct word, and the solver works. I don't usually play on my iPad, I play it on my phone. That's why the streaks won. But you can see that I can just tell the computer that we have the final answer, and now it's done. 3 guesses using this solver. It's absolutely impressive. It works so well, honestly. I can't believe it. Now, by writing all this out, by writing all the code out, it's also very nice to see which moves, which strategies we can sort of learn from the computers. And I can sort of work out which words are good first guesses to make. And this is sort of a general strategy if you're playing Wordle. So this is a list of all of the words which are apparently the best first words to play. At the very top is the word lares, which my English isn't that strong. I'm gonna be completely honest. I don't even know what that word means. I'll put the definition up somewhere on the screen right now in case you're wondering. So all of these words, on average, in expectation, in the very first round, will allow you to filter out from 8,000 different words. It will allow you to filter it down to only about 200 words on average, which is actually really, really impressive. In particular, if I take a look at the word lares and see all the possible outcomes, then you can see that about 500 words is sort of the worst case. In the worst case, you're only going to be able to filter down to about 500 or so words. Which, don't get me wrong, is still very, very impressive. Going down from 8,000 words to at least, or I should say at most, 500 or so words is still a very good amount of words you can filter out in the very first round. And in the case that you get lucky, you can see that you might filter down to even less words. You might get it down to a couple of 100 words right from the very get-go, or even in the tens if you're super, super lucky. Now, if you look at all the words which are good, you can see that there's something in common with it, and that is the fact that they all have got very common letters, right? They got the A's, the E's, the S's, the R's, the L's, the T's, right? Those words, those letters which scores only 1 point in Scrabble, these letters are common. So having these common letters is pretty good for filtering out the word from the very first go. And you can sort of contrast this with the list of the worst words that you can guess. This is a list of the worst words that you can guess. The first word, I don't even know what it means. I don't even know how you pronounce it, like zilio. I already know how you pronounce that word. I haven't looked up the definition. I probably should have looked up the definition before I came in. If I had to have a guess, it's either like it looks like a word from chemistry or biology. It reminds me of the word xylem or something, but I'm not sure what it is. I'll put the definition up on the screen. But not important. What is important is that these words are bad because of the fact that, one, they got uncommon letters, right? They got the X's and the Y's and so on. What surprised me that none of the words at the very top had the Q's, and I'm not sure why. Maybe the Q's does filter it out a bit better, maybe, I'm not entirely sure. But the other thing that it also has, it's got a lot of repeated letters. And again, that comes down to the fact that words with repeated letters are pretty rare. So, having those rare features, making a guess on and trying to filter out those, double letters or so on, it tends to not give you as much information, or it tends to not filter out enough. In this case, you can see that guessing one of these words, you're expected to have up to 3,000 or so words remaining. I mean, only filtering out about a half of the word in expectation. And that's not very good. So these are the bad words to guess, and obviously, as mentioned before, these are the good words that you can guess. Feel free to use this list to improve your Wordle game. There are also some other optimization tricks that I did for the algorithm, which I don't really want to go into too much detail. Two of them I want to mention. One is that the hints, the way that we calculate the hints, I sort of calculated all of the possible hint combinations first and then kept it somewhere so that we don't have to repeatedly recalculate the hints every single time. The other thing that I did was for the methods that we did, some of the steps, especially the very first step, is always going to be the same. So rather than recomputing the first step every single time, I just remembered which word was the single best word for the first guess and always made that move. And then I also kind of did something similar for the second step, and you can see that in the code if you take a look at it. Now, of course, there are other ways to approach this problem as well, I'm guessing. The way that I approached it was using expectation values because I thought it was simple, but expected values isn't always the best way to go, right? A lot of the times, expected value doesn't care about the variance. It doesn't care about how spread the distribution is. So something you might be able to do is maybe say, try to rank the words based on what happens, say 90% of the time. 90% of the time, it would get rid of at least this many letters or something. Or even try to optimize it through the worst case. These are some of the other possible ways you can maybe frame the problem. I also thought about if it was possible to frame the problem as something from information theory, but I think just complicates things a bit too much. I think using expected values is a lot easier to do. Anyways, that's all the time I have for this video. It's a little bit long, but that's because I don't have time. A bit paradoxical, but I think you know the quote on screen right here. Anyways, you might realize that I've not really been posting videos. If you're a long-time subscriber to this channel, you probably realize I've not posted a video on this channel for almost 2 years, and that's because I've been a bit busy. Since I last posted my video, I finished my undergrad, I went to work for a while, I applied to universities for grad school, I got accepted to grad school, and now I'm attending grad school. And you might realize the white wall, it might look like I'm still in my old house, but if you look around, I'm in a different place. Can I turn that way? Yeah, I'm in a different place. Doesn't matter. If you're not subscribed to this channel, you can subscribe. I don't know what the next video is going to come out. I have ideas, I just don't have time. But anyways, I hope you enjoyed this video. I hope you maybe learned something, maybe get better at Wordle or whatever. But anyways, thank you very much for watching this video, and I will see you guys whenever I see you, I guess.